So here we have a question from, this is section 15.7. So this is doing triple integrals and then looking at those triple integrals in cylindrical coordinates. So a quick reminder, cylindrical coordinates, when I think of those, I think of a hybrid between I have polar coordinates in my XY plane, and then I have some height above that plane. So my cylindrical coordinates are r, theta, and z. Okay, so I need to take this relationship, all the information that's given to me, and I need to find information about r, theta, and then z. So starting with this, using our polar like the polar information that I have, the question I picked out, these are the three different equations that they give us in the question, along with the integral of x squared dv. So starting with the restrictions, the first restriction I have is that I'm within the cylinder formed by x squared plus y squared equals 1. So that means that all of this is going to happen inside a cylinder of radius 1. This in polar is r squared equals 1. So that means if I'm within that cylinder, that's going to give me a bounds for my radius of between 0, that's a 0, not a weird looking 6, between 0 and 1. The next thing, so now I have a radius bounded. I need to think about z and about my theta. Thinking about z, let's go ahead and address z first with the next two equations. This part right here tells me that z is going to be greater than 0. That means that I'm only looking at information that's above the xy plane. That's important because when I solve this, that allows me to take the square root and only think about the positive square root. I don't have to worry about the positive and the negative root. So here, I can rewrite this. So that's going to be 4 times x squared plus y squared. So that means that z squared is equal to 4r squared. So now, since I know z is positive, I can square root this and get that z. So if I'm below that relationship, that means that z has to be less than 2r. So here I can write this between this, above means greater, and then below means less than. So it's going to give me my relationship between z, which is a good relationship to have, because if I notice, when I do this, I need to start and rewrite my variables so that I'm then bounded by the other ones that I have. So if I take out z and I do an integral and replace it with 2r, then that means that my next integral in terms of r, I can replace that. So like the variables match in that elimination process. The other thing I don't have anything for my theta. So if I look at the restrictions, or if I think about what this space is representing, is I have a cylinder that's going up above the XY plane. So I'm cutting it off. So I have a cylinder above the XY plane, and then I have a cone that's starting at the origin and going outwards. So I need to think about the angles. Well, to make the cylinder and to make the cone, my angles are going to start from 0, and they're going to go all the way around the circle to 2 pi. So that's going to create that, the whole space for me. So I'm going to take 0 theta, and it's going to go up to 2 pi. So those are my bounds that I'm going to use. Let me take this now, and let's rewrite this integral so that I'm in terms of this information. So I'm going to go from 0 to 2 pi. That's my theta. My radius is going to go from 0 to 1. And now I have z, which is going to go from 0 to 2r. So now when I write out my integrand, I need to remember in cylindrical, I still have this relationship. X is equal to r cosine theta, and y is equal to r sine of theta, with what we used earlier, x squared plus y squared is equal to r squared. So when I go ahead and write this, I can't leave x squared. I need to rewrite that. So that's going to become r squared cosine squared. And now my dv, so I remember when I use polar gives me r dr d theta. I have r, then I'm going to put dz dr d theta. So this is my Jacobian, my change of variables, my change of coordinates. I pick up that r. So again, like we said earlier, this is a combination of kind of polar in my xy plane and then some height z off of it. So that's why we're using these. These are my three variables that we're talking about when we do something in cylindrical, okay? So now looking, we're gonna start, let me go ahead and write this over again, simplify what I have. So here we have an integral. Theta goes from 0 to 2 pi. My radius goes from 0 to 1. My z value goes from 0 to 2r. Just combining like terms, so it's going to be an r cubed cosine squared, and I'll do dz, dr, d theta. So again, just real quick about the list, the order that these go in, I want these to match the information that's out here, right? Starting from the inside and then kind of like peeling off towards the outside. The other thing I need to keep in mind is since 2r is one of the limits of integration for z, that means I need to integrate z before I integrate r, okay? I don't want to have an integral here on the outside that has some variable left in it that isn't going to get taken care of in my evaluations, okay? So that's what we're going to start to integrate. I'm going to clean up the board. So if you want to go ahead and do a couple steps, you can pause right here and then push play again to have it check your work. But I'm going to pause and clean up real fast. So here we are with the board cleaned up. I'm going to start integrating. I'm going to start with this first inside integral with respect to z. So I notice here, I have no variables that are z. So this is just some constant. So I'm just going to carry that down, r cubed cosine squared theta times z. I'm going to evaluate that from z equals 0 to z equals 2r. Here, awesome, I have 0 again. So when I plug in a 0, this just goes away. So all I really need to do is plug in 2r. That's going to give me 2r to the 4th cosine squared theta. So now this is going to become my next integrand. So let's go ahead and write out the next step. Feel free anytime or any part along this if you want to pause and work ahead so that you can see if you can do it on your own and then check your work, that's fine. I won't even know. So here, 2r to the 4th cosine squared theta dr d theta. So that means that now I want to integrate with respect to r. Let me highlight that right here. I'm going to work inside with this integral. So the cosine squared, this is just a constant along with the 2. So this is what I'm taking the antiderivative of is r to the 4th. So here, this antiderivative, I'm going to get 2/5 r to the 5th cosine squared theta. I'm going to evaluate that from r equals 0 to r equals 1. Again, so when I evaluate 0, this is just going to go away. So when I plug in 1, I just get 2/5 cosine squared theta. So then this is what I'm going to go up here, and I'm going to plug into the next integral, okay? So my final integral, we're going to have, I'm going to take the integral up from 0 to 2 pi, 2/5 cosine squared theta, d theta. So then the next thing I'm going to do is I need to rewrite this. It's going to become, so remember, our double angle formulas, our power reduction formulas. This is from Calc 2 or from your trig class. This is going to become 1/2 of 1 plus cosine of 2 theta. So that's this part, cosine squared. So this 1/2 and the 2/5, the 2's are going to reduce. So I'm going to end up with 1/5, the integral from 0 to 2 pi of 1 plus cosine of 2 theta, d theta. So now I can talk about an antiderivative. I'm going to have 1/5 times this antiderivative is going to be theta. This antiderivative is going to be sine of 2 theta over 2. There's a plus in between there. I'm going to evaluate that from 0 to 2 pi. This works out kind of nice because here, when I evaluate sine at 2 pi, that's just 0. When I evaluate sine at 0, or 4 pi, when I plug in 2 pi, I'll get sine of 4 pi. That's going to be 0. When I plug in a 0, I'm going to get sine of 0 is 0. So all that is 1/5 times 2 pi. So that's going to be 2 pi over 5. So that's an example, an idea using cylindrical coordinates. Keeping in mind that I'm using r, theta, and then z, some height above the xy plane. It's a weird kind of combination of the two. But anytime I'm bounding myself inside, if I'm using cylinders to bound myself, it's obviously cylindrical coordinates would be great using with cylinders. It also works well with cones, anything that has the x squared plus y squared. And it's, again, you're looking at your region, what you're integrating over to let you know how you're going to switch or what coordinate system you want to use. So there's an example. That's number 21 from 15.7. If you got questions, please go ahead and send me an email and let me know how I can help you. Okay.